Hello, this is Ayush, and today I am going to be presenting the work MimicGait. Uh, the task is Occluded Gait Recognition, and this work has been published to WACV 2025. So the task we are solving here is gait recognition, which basically is a person re-ID task. Um, Gait refers to the way of walking, and it consists of various parameters which we can measure through sensors. But vision-based gait recognition is a more practical approach to re-ID, where we just try to recognize the person just from videos, which might be potentially captured at very long ranges. And when face and body are not available, gait can be a more practical approach for person re-ID. And generally, gait recognition is performed on silhouettes. If you have RGB data, you pre-process it to convert to silhouettes. This is done to avoid the effect of covariates like clothing color and background. So like all computer vision problems, occlusions are a major problem within gait recognition too. And of course, if part of the input is missing, the gait signature generated by the model is corrupted. And most current works don't do anything specific to address this problem explicitly. And in this work, our aim is to tackle this problem explicitly. There has been some previous work on this problem, specifically this occlusion-aware gait recognition work. The idea behind this is that like knowing the occlusion type can actually help the gait recognition network to learn better features. How they do this is they use an auxiliary occlusion detector network here D to in a pre-training stage to learn to classify different types of occlusions. And then when they are training the gait recognition backbone, they use the same occlusion detector D and insert this occlusion relevant information inside the gait recognition network. So the gait recognition network becomes occlusion aware, and they show that it helps generate better features. So the motivation, moving on to the motivation for this work is we observe that gait patterns and different body parts are correlated, right? So there is redundancy in the motion of different body parts, like the right arm and the left leg, they always or usually move together. And we can try to learn these correlations and exploit these redundancies. So when one body part is occluded, its motion pattern could be obtained from the motion of other visible body parts. And previous works on the same problem do not utilize this idea. However, this idea can be combined with the occlusion detector of the previous work. So this is the idea of our approach. We utilize a student-teacher setting to train something called the mimic network. So initially, the teacher network is trained on complete inputs, holistic inputs to generate ideal features. The teacher network may be any state-of-the-art gait recognition network. And in the later stages, mimic network tries to mimic or copy these ideal features. So these triangles are ideal features and these circles are the mimic features. And through our approach, we try to make the circles, which are generated through occluded inputs, come closer to the triangles, which are ideal features. This is a model agnostic approach. Like any state-of-the-art network may be used with this strategy. And we also utilize, like the previous work, we also utilize an auxiliary network to guide the mimic network. So through our loss function, we need to bring the mimic and the teacher features close together in the latent space. And like one basic approach is to use L2 loss between these two features. We can call this like simple L2 distillation loss so that the mimic network and the teacher network's embeddings will come closer. However, in our approach, we use multiple positive instances. So instead of student-teacher learning within the same instance, we will use different videos of the same subject and we'll also use them as positives in our loss. And of course, we'll use samples from other subjects as negatives. And through our experiments, we demonstrate that utilizing multiple instances like this helps the mimic network learn better features. Hence the name multi-instance correlational distillation loss. So how do we evaluate our work? We use something called rank retrieval, which is basically the most common metric used to evaluate gait recognition tasks. Basically, the test set is split into two sets, like gallery, which is labeled, and a probe set. So gallery is the database of all the known subjects which are enrolled in the system, and they have gait sequences of all of these subjects. The task is to match an unseen probe to one of the elements in the gallery, and the accuracy of this matching is called rank retrieval accuracy. However, rank retrieval accuracy is an absolute measure of performance, and it depends on like multiple factors like the difficulty of the data set, the strength of the backbone network, or maybe the difficulty of occlusions. However, we want to evaluate a model agnostic approach like MimicGait. We don't want the effect of the backbone architecture. We don't want the backbone architecture to have an effect on the evaluation of the model agnostic approach. Let's say like a stronger backbone should not give false impressions of improvements. So to disentangle the strength of the backbone with the strength of the occlusion mitigating method, like MimicGait, we propose a new metric called relative performance, where we normalize the occluded rank retrieval accuracy with a measure of the strength of the backbone, the raw strength of the backbone. And that's how we come up with this new metric. And more details can be found in the paper, but yeah, this metric is a little bit better in disentangling the effects of these two. And so finally, here are the results. The exact numbers are not important in this huge table, but the Mimic network outperforms at the baselines for occluded gait recognition, and we can see this for like multiple data sets as well as multiple backbones. It outperforms most of the baselines proposed in previous work, and the new metric relative performance can reflect improvements in cases like this, where the absolute accuracy is very low due to a suboptimal backbone architecture, or maybe due to a very difficult data set like this. But relative performance captures that the data set is actually also very difficult. So it normalizes this, and we get like decent numbers even in the relative performance metric. So these are the ablation experiments where we evaluate each of the individual components proposed separately, and we have three components, right? The mimic training strategy, or also called the multi-instance correlational distillation loss, and the two proxy tasks we use to train the visibility estimation network. We through our experiments, like we observe that each of these components individually contribute to performance, and when we use all three, we get the best performance. So that was it for the overview of this work. Here are some limitations, like we only evaluate on synthetic occlusions here in our work, and adapting to real occlusions may not be as straightforward, because the datasets we have, they do contain some real occlusions, but not in a separate occlusion class. I mean, the occlusions are scattered across all of these sequences in the dataset. The current formulation of the mimic network also requires paired data in the sense like you would need an occluded version and a complete body version of the same person. And while this is possible for synthetic occlusions, it is very hard to get from real data. We also proposed a model agnostic approach for occlusions. However, maybe creating a network architecture targeted towards occlusions might perform better. So who knows? And so these are the references, and thank you for listening. More details can be found in the paper or on the project website.